The next topic we're going to get into is earth structures. This section has two subtopics: slope stability, which covers the stability of infinite slopes with and without seepage, and the stability of finite slopes in clay. The last subtopic will be slabs on grade. Since we don't really anticipate you having to design a slab on grade, this will be just more of kind of an introduction to them and talk about some rules of thumb for it. So getting into slope stability, this is a picture from the El Salvador landslide that was caused by an earthquake in about 2001. And so just kind of give you an idea of kind of what can happen. And so earthquakes can cause landslides, and a lot of it has to do with the vibrations can actually shift the particles in the soil and actually cause shearing. However, this kind of diagram right here kind of indicates this is a rotational failure, which is a rotation or a failure here at the toe. So the toe would give way, and the rest of it would cause a chain reaction and push a lot of the fill material out into the village down here. This is, I believe, claimed about 600 lives just from this landslide alone. So it is a huge deal, and it's even big in the United States. This is actually from the I-75 landslide, and this happened, I believe, in 2012 and was just finished being repaired here in 2013. And this actually cost about $10 million to repair, and it affected about 200 feet of actual highway and about 250 feet down. So this was a huge issue, and this was actually caused by erosion from what I read in the reports. And so if you notice, it actually took away a lot of the lanes here. So these are some key issues we have to consider when we deal with slope stability. Is with landslides, they can be caused by erosion and weathering, and they can also be caused by earthquakes, as seen in the El Salvador issue. But we'll get into a few more of the causes of them here in a few slides. But these tend to be the major modes of slope failure. So we have rotation on a curved slip surface, and so this is that rotational failure I showed on 2 slides ago. And then we also have a translation on a planar surface, and this tends to be when the angle of incline is greater than the friction angle. You tend to see more of this happening, and this will be more on your cohesionless soils. You'll see this a lot. And then we also have a displacement of a wedge-shaped mass, i.e. like a rock slide or something like that, and this could be just done through excess loading or something like that causing this to occur. And essentially it'll just be an edge here, and it'll just fall off and then start toppling down. So cause of the slope failure, there's a few main causes. One is changes to the slope profile, which can actually be caused by erosion and weathering, or it can actually be a man-made cause, i.e. someone put more soil on the slope than was originally there, and that can cause it. So that can even be caused by construction activity, could be an issue, or potentially vibrations from blasting as well. Some of the methods we'll use to stabilize some slopes is we can reduce the actual slope itself or reduce the height. And what that will do is actually reduce the actual amount of material that could potentially slide. Then we could also create a bench in the slope. So what we'll do is we'll break up the slope. So we'll have a slope coming down here, create an actual horizontal bench, and then continue the slope down. Another way we can do it is to either use piles or to build retaining walls. And typically at the toe, this will occur. So the retaining wall will basically help strengthen the toe to prevent a lot of the rotational failures. And then we can also use earth and rock anchors, and we can also use some erosion control measures to basically prevent weathering or deterioration of the slope. So getting into stability of infinite slopes, a question you may see is calculating the factor of safety of a certain material. And so if I'm looking at this layer right here and I'm concerned about its stability and not sliding, what we're going to look at is the cohesion of the soil, and we'll look at the friction angle of the soil compared to the unit weight, the height, and to the inclined angle. And so those are the only variables to be considered here. A couple points of emphasis here. Say I have a cohesionless soil, this term will go to 0, and then suddenly it's just up to the friction angle and the inclined angle to determine whether this is going to fail or not. And so this also gets into, sometimes it's called the angle of repose, and that's kind of what this is getting into. Say if this was a sand layer and I increase the incline above the internal friction angle, this is actually going to slide off and fall. However, if I maintain the inclined angle below the friction angle, I'll maintain a factor of safety. Conversely, if I have a soil that has almost no internal friction but has high cohesion, then I'll only be dealing with this term here. So with clay, as it typically is the case, we just kind of assume the friction is zero. However, with sand, it's typically the opposite, where we assume cohesion is practically zero and the angle is such. So then we can also get into seepage, where we'll actually have to change our unit weight. Instead of using just the regular unit weight of the material, we'll have to use the saturated unit weight or the effective unit weight, just depending on which portion we're actually dealing with. So as you can see here, just as a reminder, the effective unit weight is equal to the saturated unit weight minus the unit weight of water. So getting into the stability of finite slopes with clay. And so with this clay layer, what we'll wind up doing is we'll have a rotational failure. So the rotation will basically follow this plane and come out over here, and it'll be a rotation about this toe point right there. And so the way we actually are going to look at this is we're going to take the factor of safety is equal to the stability number times the cohesion divided by the unit weight times the height h. And so you may be asking yourself, what's the stability number? And that's where we'll get into using this chart right here. And so with the stability number, what we're going to wind up doing is going in there with dh and h and figuring out what the value of d is by basically figuring out what h, or knowing what h is rather. And so what we wind up having is, if d winds up going to infinity, which this becoming the impervious or impermeable layer down here, or the bedrock or so. So looking at the stability of finite slopes in clay, what we'll wind up doing is we'll have a clay layer here above a firm layer. And so the failure plane in this finite slope will actually come from here and then be kind of a curve around here, with the failure point centering around this toe point right there. And so the factor of safety for this will be equal to the stability number times the cohesion divided by the unit weight times the height, and the height is h right there. So the stability number will have to be interpolated from this chart. And so using this chart, what we'll do is we'll use the dh and h relationship to figure out what the value of d is. And so depending on the value of d, we'll change up where we are in the curve. And so say if d is infinity, as in the clay layer basically goes infinitely deep, or at least greater than about 3 or 4, then we'll wind up down here. And so we'll come across and figure out the stability number is about 5.53, and we can calculate it right there. However, if dh is at the same level as h, then it'll bring our curve up to here, and it'll increase our stability number. And this also is dependent on the slope inclination as well. So probably one of the more key things I would take away from slope stability is the recommended factors of safety, and I would definitely write these down somewhere if you don't already have them. So with slope stability, for permanent loadings, we're looking at a factor of safety about 1.5, and slope supporting structural foundations at least 2, temporary loadings about at least 1.3, and then transient loads, i.e. loads related to earthquakes, about 1.2. And I would say these are probably the absolute minimum I would use. However, obviously you could use higher factors of safety depending on what you were doing. But I would say these are probably the minimums that I would use. So talking about slabs on grade, I don't remember even having a slabs on grade question from my exam. I asked other people, they don't remember them either. And I've looked through the all-in-one handbook and the CE reference manual, and nobody even really covers slabs on grade. So as far as I can tell, essentially what they're going to ask you about is conceptual stuff. And I think it's going to be more of stuff like, with wire mesh, where does the wire mesh go in the slab? And the answer you'd say is wire mesh goes closer to the top because wire mesh is meant to prevent cracking. However, if I was going to make this a reinforced slab with actual rebar, the rebar would have to go towards the bottom where more of the tensile forces are. And typically with slabs on grade, they're also bedded, and that can be either on a gravel layer down here or basically something that allows water to flow through. And then another question you may see is when are vapor barriers needed below slabs on grade, and basically if it's in a basement or something like that, somewhere where people can easily see it, you would use it. If it's out someplace where no one's going to notice it, then you may not need it. So those are probably the key takeaways I would go with it. With slabs on grade, one other way you could look at it when you start talking about the actual grade beam down here, this beam will actually be thickened on the edge. And so typically on the edge of a slab, you'll see this type of thing, unless you have a actual strip footing going on as you see in this picture, in which case then these will just butt up against each other, and they may be anchored in as well. If you want more information about concrete floor slabs, then I would probably look at this reference. And the main reason I say that is because it's a free reference and it talks about reinforced and unreinforced plain concrete. So if you want to get some more information to feel more comfortable about it, I would look in here. However, I really can't see them asking you too many questions about this, so I wouldn't stress too much about the slab on grade on the exam specification.